Hi, this is an example problem, energy calculations from an equipotential map. So in the previous problem, we saw how to solve problems involving energy using the electric potential. The electric potential can take different shapes. It's generated by charges, so you can see there's a source charge there in the middle of the picture. But if that source charge is fixed and just stays there, nothing happens with it, it generates this landscape of electric potential in the space around it. One way to view that is to draw what we call equipotential lines or surfaces. And these are regions in the space, surfaces, or in two-dimension, in a profile cut, lines, where the electric potential has the same value everywhere. We can use this map to do energy calculations, similar to what we did before. Remember that the electric potential energy, it's equal to a charge Q0 that is multiplied by the electric potential located at the position where the charge is at. We can also figure out the work done by the electric force by doing minus the change in the electric potential energy. Pause for a moment to read this question. All right, so this one's going to be kind of quick, and you'll see how, in a way, this is kind of an easy thing to do, and the units are important to look at here. So we've labeled the equipotential lines in terms of volts, 4 volts, 6 volts, 8 volts, 10 volts, etc., right? But it's important to remember that volt, it's a unit for electric potential, but it's also equal to a joule per coulomb. And a lot of times the joule per coulomb is a better one to use because it gives us more meaning. What is the potential energy of a charge Q0 at point A? So I'm not talking about the orange charge. I'm going to take another charge and I'm going to stick it at point A. All right. This is Q0. It has a value of minus 10 coulombs. Now, because it's been placed near the positive charge there, it experiences that electric potential at point A, and it is going to have an electric potential energy, and we can calculate that like this. Potential energy of the charge Q0 at point A is going to be equal to the charge value Q0 multiplied by the electric potential at point A. So we're going to have minus 10 coulombs, and the electric potential at point A is equal to 8 volts or 8 joules per coulomb. The electric potential generates or creates an electric potential energy for that charge Q0. It's going to be equal to minus 80 joules. So 8 joules for each coulomb. We put minus 10 there. We get minus 80 joules potential energy. Let's look at part B. What is the PE of Q0 at any point on the equipotential line that passes through point B? All right, let's go ahead and move Q0 so it's no longer on point A. And we can put it somewhere else. Remember, we're not doing anything with the source charge. It's there. It creates electric potential. Anywhere through point B, right? So anywhere on point B, we've got electric potential of 6 volts. So I can go right here if I want. I can stick the point charge right here. It's on the same equipotential line as point B. It's going to have 6 volts at that position in space. What's the potential energy there? Let's calculate it. We are on the B equipotential line, so we're going to have 6 joules per coulomb at that location. Of course, we cancel those coulombs out, and we're going to have minus 60 joules of potential energy at that position. Let's look at part C. Calculate delta PE if Q naught is moved from point C to point A. So say we're over here, we start at point C, and we're going to go ahead and move it around. Doesn't really matter how we do it, but it's going to end at point A, right? So it's going to end there. It's going to start here. All we care is about the start and end points because we're calculating a change in the electric potential energy. And so we start at C, end at A. A is final, so it's going to be PA minus PEC. But hey, look, C is the same electric potential is B, so we know it's 6. In fact, we know both of these, right? C is the same as B. And so therefore, PA is going to be minus 80 joules from part A, minus from part B, it's going to be minus 60 joules. And the double negatives end up giving us a minus 20 joules change in the electric potential energy of Q naught as it moves from point C to point A. Let's look at part D here. How much work is done by electric force in part C? Well, we're going to use this formula. The work is equal to minus the change in potential energy. And so we're going to get minus a negative 20 joules. That'll give us 20 joules of work done by the electric force. So that means that the charge is, in a sense, it's gaining some energy if it goes from C to A. If we just kind of somehow got it from C to A, the force does some work. All right, now in part E, we're going to consider how this charge would move, this Q0, if it were placed at point C. So we've got it at point C again here. And we're going to consider how is it going to move if we just release it from rest. So here it is, point C. Where do you think it's going to go? It's a negative charge, right? Well, it's going to be attracted to the positive source charge. It's going to move straight up towards that source charge. That's what we can expect. So up, that's the right answer there. And let's think about it for a second. Notice that it's going to start here at a value of 6, right? Right here we've got 6 volts. And it's going to move towards a higher value, 10 volts, right? So this is a general rule. If you have a negative charge, they will spontaneously move from lower to higher electric potential. It's exactly opposite for a positive charge. A positive charge will spontaneously move from high to low. The reason why is because the potential energy always going to decrease any time that you have spontaneous motion. Now, for a positive charge, if you go downhill in the potential and you calculate the change in potential energy for a positive charge, if the, here's your change in the electric potential, or your voltage. If this is going to go down, then naturally the electric potential goes down. So a positive charge is going to go from high to low, and that reduces its electric potential energy. On the other hand, if we have a negative charge, well, the Q is going to be equal to a negative value, right? So what we got to look at in this case is consider Q being negative. We got to make the change in the electric potential go positive, right? Because multiplied by negative Q, that's going to reduce. That's going to cause a negative potential energy. Change the potential energy decreases. So in this case, electrons do the opposite of what you expect. They spontaneously move from low to high electric potential, which reduces their electric potential energy. Turns out that they made a decision back in the day to set everything up the right way for positive charges, so everything is going to be opposite for negative charges.